and welcome to section 5.2. So we're going to start getting into it in this section, talking about integration, which is what chapter 5 deals with. So this section is still going to be a more building process up to the concept of integration that we'll get into more so in the next section. So again, we're building on these sort of approximations, trying to get to a better way to evaluate area exactly and talk about the antiderivative and what it really does for us. So again, 5.2, this section might be a little involved, but don't worry, it's not like it's getting more and more complicated. We're building off these complicated processes in order to say, okay, is there a way we can generalize this and make this a little bit easier? With the answer being yes, of course. So in future sections, it's not going to be as tedious. Might be a good word to use. So I'm going to start this section off with the definition. And what we'll do is we will say, let f be a function on the closed interval a to b, or let's say let f be a function defined. You don't want to run into any sort of trouble areas. So we'll let f be a function defined on that closed interval a to b. We'll divide up, or so we'll say let that interval a to b be divided up into n subintervals of width delta x, which we can compute by taking the entire interval and dividing it up n times. So again, b is the end point, a is the starting point for our interval. That entire length will be b minus a, and if we want n subintervals within that entire interval, we'll just chop it up n times, right? Divide by n. Next, let a equal x0, x1, x2, comma, dot, 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 all the way up to xn, which will be b. So basically what we're saying is the first x value we use is the starting point on our interval, and the very last xn, right? We're not going past n because we're only using n subintervals. That very last xn is going to be b. So we're going from a to b, starting with the first one. This just says a is the first x0. Then we pick up the next, then the next, then the next, et cetera, et cetera, et cetera, and only the last one is b. Right? Be careful, this notation is not saying that a is equal to x0, x1, x2, xn, and a is equal to b. That's not what that notation is saying at all. So we are going to let x0 all the way up to xn, starting with a as the leftmost endpoint, b the rightmost endpoint. And each one of these is an endpoint of each subinterval. And let xi star be any sample point in each of these subintervals. So we've seen that star notation in the last section. Again, that's just going to be any sort of sample point that we decide to take. Could be the left endpoint, midpoint, right endpoint. I actually have some choice there. Then the definite interval. Try to get that to look a little nicer. There we go. The definite interval of f from a to b integral from a to b of f of x dx, which is going to be computed by finding the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x. And we've seen this notation before. I'm actually going to throw in, since we're using that xi star, I throw that xi star in that notation as well. So this is what we call the Riemann sum. We use that Riemann sum to build the integral. So if this limit exists, we say that the function f is integrable. Integrable. Spell that right. On a to b, or I should say on a to b, we'll do the interval notation. On the interval a to b. So a whole mouthful there to basically say that in the last section when we looked at approximating areas, what we did was we had a whole bunch of rectangles, and we had to go through those rectangles and try to approximate the area using left endpoints, right endpoints. So here is what we're defining, the definite integral of f from a to b. So when we look at this notation now, we'll get this definition out of the way. There are some things that we can say about this notation. So this is a definite integral. There will be some sort of function plugged in there. That function, f of x, is what we call the integrand. That is the thing that we are required to integrate. So they'll be giving you a function and they'll say, hey, integrate this function. That's where that function goes. You will also have these limits of integration, a and b. Specifically, you will have a lower limit of integration. Some people call this a lower bound, right? You might say that as well. A lower bound. The upper limit of integration, again, some people might say upper bound. They mean the same thing. This looks like a little string of spaghetti here. This is what we use for the notation for the antiderivative. So when we integrate a function, we use this to say, hey, it is your job to integrate. So this is just the symbol used for the operation of integration. Just like when you take the square root of something, there's this radical bar notation. This bar tells you, hey, you, take the square root. That's all this tells you is, hey, you, take the integral. So it's just signifying to you, the reader or the person solving the problem, what you really need to do. Right now, this dx doesn't really have much meaning for us, but it does have meaning. We do have to put it there. It does have to be there. Without it there, this is very meaningless. That dx is just telling you what variable we integrate with respect to. The variable that we integrate with respect to. So it's not telling you that f of x is being multiplied by dx or something like that. It's just saying that you have a function f, your job is to integrate it, and you say, okay, with respect to which variable? Well, since we're only dealing with single variables for now, it's obviously got to be x, but we do need to identify it. If you take Calc 3 and you have multivariables, a function of x, y, and z, and they tell you to integrate with respect to y, you better not be integrating the variable x or the variable z. So that is very important down the road. right now, right, we got our training wheels on, so we can't fall off the bike. We can only integrate with respect to x. So sometimes in Calc 1 students get lazy and they don't write that. If you don't write that, you are completely wrong and you're just abusing the notation. It's just like, misspelling words in English, or it is like mispronouncing things in Spanish class, right? You're getting it wrong. There's no way around it. So you have to write that there. But for us right now, this notation is brand new, but we're going to be using it for the rest of the entire chapter. But in this section, we're still going to be dealing with some of those Riemann sums. We want to build off of those, the concept of the Riemann sums in order to get to this integration, which is, again, we start with the more complicated stuff to try and come up with a more general theory. That theory will be the fundamental theorem of calculus when we get to it. But once we get there, then things become a little bit easier because we've gone through the muck of trying to prove that this exists, or that this is always true. Once we've got that under our belt, we just use that theorem and things become easier. But we got to get there first. So, I'll just squeak it in here because there is space. So here is the theorem that if f is continuous on that closed interval a to b, then f is integrable on that closed interval a to b. So any continuous function is going to be integrable over that interval where it's defined, right? We can actually extend this a little bit further. If f has finitely many what they call jump discontinuities, like piecewise functions exhibit this quite a bit. Then f is still integrable on a to b. All right, so even if it has some discontinuities, we can actually still integrate it. And again, those jump discontinuities means if I have a function that goes like this, and then jumps up here and goes like this, and my goal is to integrate it from a to b, it does not affect my integration. I can actually still do the integration, which is actually really, really powerful stuff. Not that we will probably come across that in a Calc 1 course. We may if we encounter a piecewise function, but more so, later on if you get a little bit deeper into some advanced calculus, or maybe start doing some analysis, you can show pretty nicely that that integration from a to b, that is from here to here, especially if you're trying to relate it to a concept like area, it's nice to maintain that we can still do that integration. That is a very powerful thing. But mostly for us, we're going to be dealing with, a continuous function and just applying it to the concept of area, or just simply finding the integral, right? So, good theorem to have. As long as we're dealing with a continuous function and we don't have to sweat anything, we can integrate it. That's all we need to know. Right? If it's continuous, or if it has a finite number of jump discontinuities, we're still going to be able to integrate that thing. So now we want to tie these concepts together using the Riemann sum and the new notation. So we'll say if f is integrable on the closed interval a to b, meaning i.e. it's continuous or it only has a finite number of those jump discontinuities, then the integral from a to b of f of x dx is going to be equal to the limit as n goes to infinity of the sum from I equals 1 to n f x of I star delta x. And we'll start to label how to find these things where delta x, that is the change in x, is b minus a over n. So we're going to take the entire interval from a to b. The length of that interval is b minus a, the upper minus the lower. That's the length of the entire interval. And we want to chop it up n times and then let that number n go to infinity so that we divide it up an infinite number of times. Basically, we're building an infinite number of rectangles underneath that curve, if you relate it to that concept that we saw before. And x of I is going to be found by starting at the beginning of the interval and then adding each change delta x to it. So starting at x1, right, I would be at a plus x1. x0 would be, well, this would be 0. I'd start at a. And then I go to x1, so I get a plus that little bit of change. Then I get x2 would be a plus 2 of those little bit of changes. So I keep moving and moving and moving further and further down my interval until I finally get to xn, which if you look back at the other notation, x of n was a plus n of those changes in the x value gets us all the way to the endpoint b. So we start with, x0 is going to start here and just have us go through and find the actual beginning of the interval until we go all the way up to xn and get to the end of the interval. Again, the notation's a little thick in the beginning of chapter 5. Our goal really is to get to this integration notation so that we're not dealing with limits and sums and finding these weird sub-intervals of intervals. Right, so our goal is really to get to this integration notation. But again, we got to kind of get through the muck first. So before we do an example, I want to give you a little reminder on some helpful properties or rules, whatever you want to call them, of sums. This is stuff that we should be able to recall from pre-calculus, or if you've done anything with some summation notation. This is going to be a little familiar here. Now, I'll keep them numbered. Not that they're numbered in terms of importance, but just numbered. So if you want to number them to refer back to them a little easier, you can go ahead and do that. So if we sum up I from 1 to n, that is counting up the numbers 1, 2, 3, 4, 5, 6, 7, blah, 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 all the way up until a very specific number. Say we want to count up and add all the numbers from 1 to 100. Well, that would take a while. We do 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus, right? So you'd have to sit there and do 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to plus 100. Well, rather than do that, we can just use a really nice formula. If I want to sum the numbers from 1 to 100, all I have to do is take the number 100 here, plug it in. 100 plus 1, divide by 2. So 100 divided by 2 would be 50 times 101. So it makes things just a little bit simpler as far as the computation goes. Now, I'm not going to give you a whole list of just these, but the ones that we encounter the most are just the sum of all the numbers from 1 to n, the sum of the squares of those numbers. That means I'm adding 1 squared, plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared. Right? That's already getting pretty huge there. We're going to have to add up the values of n times n plus 1 times 2n plus 1 and divide by 6. So a much faster way, if I want to sum up the squares, I just take whatever that number n is and I just go ahead and plug it in. If I want to sum up the cubes, and we'll stop there. You can keep going to 4th powers, 5th powers, 6th. But again, we don't want to do this forever. We want to get to integration. So that's why I'm not going to focus too heavily on this stuff. This one's actually pretty nice to remember, too. All you have to do is square this formula for the sum of the integers from 1 to n, and you actually get the cubes formula just by squaring everything up top and squaring the bottom. So that gives you the formula for the sum of the cubes. Like I said, you can come up with formulas for sum of 4th power, sum of 5th power, sum of 6th powers, but that's just going to trail on and on and on and on, and we don't want to do that forever. We don't want to keep memorizing a bunch of formulas. We want to know how to do the math. So This is, again, coming from more of a pre-calculus refresher, really, is what we're doing. If we sum up the constant from 1 to n, then all we have to do is multiply that constant by n. This constant is just a number. Say it's the number 5. So I'm summing up from n equals 1 to 5 of the number 5. Well, there is no I here for me to sum up. I'm just looking at the number 5 for the first one, 5 for the second one, 5 for the third one, 5 for the fourth one, etc., 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 all the way up to 5 for the nth one. So all that is 5 plus 5 plus 5 plus 5 plus 5, dot, 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 all the way until you get to 5 again at the end, and you're just adding 5 up together n times. That's the definition of multiplication, right? 5 plus 5 plus 5 is 3 times 5, right? You just added 5 3 times. So if there really is no I here or anything that you need to worry about in terms of adding up an I and summing it all up, then we just multiply by whatever that number is. So this you might even want to call like formula 0 that comes before an I even exists within our sum. But the book labels it sort of in this pattern, so I'm trying to sort of, stick to their pattern. If we sum up C times A sub I, where AI is going to be a term in a sequence, and then we're just going to sum up each one of those terms. More importantly here, this is just a property of summation notation. I can take that multiple of C out, because rather than multiply every single term by C, like C times A1, C times A2, C times A3, C times A4, well, they all have a common factor of C, so I could factor out that common factor of C, and then just add up A1, A2, A3, A4, A5, and when I'm done adding all those up, I just simply need to multiply by C, because it's simply just a nice scalar multiple. So multiplication works really nicely with that summation notation. Also, if I have two finite sums, but I'm adding or subtracting these different terms in here, then rather than do it all in one big chunk, I can sum up across all the AIs, and then depending on whether it's addition or subtraction, sum up across all the BIs, whatever those terms are. Right, so rather than doing A plus B, or A1 plus B1, A2 plus B2, A3 plus B3, A4 plus B4, I'm adding anyway, so I might as well just do A1, A2, A3, A4, A5, A6, A7, and then when I'm done adding those, add B1, B2, B3, B4, B5, B6, B7, right? So you can still add them up. And the reason we can do that and break these up is because they are finite sums, right? These aren't infinite sums. So we're okay there. We're only adding up to a finite n. When you start talking about infinite sums and you start trying to play this game of breaking things up, danger, danger, right? Because infinity doesn't like to behave nicely. So again, notation's a little thick, but this is actually old stuff that we've seen back in pre-calculus. So you'll use some of these formulas in the problems when you're, summing up some squares or summing up some cube terms. You'll use some of those formulas in the exercises just to speed things up. Right? So now let's take a look at an exercise. And this is an example of, a problem we're going to do two different ways. So first, we want to evaluate the Riemann sum. For f of x is equal to x squared plus 2. And they'll ask us to do that by taking sample points to be right endpoints. So not left endpoints for the rectangles, not midpoints. We'll just stick to the right endpoints. And starting at a is equal to 0, that's the beginning of the interval. b is equal to 3. That's the end of the interval, so we're going from 0 to 3. And they want n, which is the number of rectangles that we use to approximate, to equal 6. So they're giving you an interval from 0 to 3. They're saying, hey, n is going to be 6 in this case. We want 6 subintervals, right? So that means we got to chop it up into 6 rectangles. So the way we do that is, well, our notation has us find the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x. Well, delta x is the change in x, and since I'm breaking it up into 6 subintervals, I need to take the entire length of that interval and chop it up n times. That is to say, I need to take the entire length, which is 3 minus 0, and chop it up n times, which is chopping it up 6 times. So my delta x, in this case, is 1/2. Now, to calculate the endpoints, again, I'm using right endpoints. So when I go to find my xi's, they're going to be of the form a plus I times delta x. Well, I'm starting at the right endpoint, so I want my first right endpoint x1 to be given by a, which is 0, plus 1. Since I'm looking at x1, I want 1 times delta x, which is 1/2, which tells me that x1 must be 1/2. x2, I can find similarly the same way. It's 0 plus 2 times 1/2, which is just 1. Right, and we can keep going with this process. Notice that every time I'm just adding 1/2 because that's the change in x. So each rectangle is going to have me move 1/2, 1/2, 1/2, because each of those 6 rectangles is going to have a width of 1/2. And I want right endpoint, so I'm not starting at 0, which is a left endpoint. I'm starting at the first right endpoint, so I'm moving that 1/2 distance. Then I move another 1/2. Then I move another 1/2 to 3/2. Then I move another 1/2 to 4/2, which is 2. Then I move another 1/2 to 5/2. Then I move another 1/2. And I'm at my right endpoint for the 6th rectangle. I should be hitting the very right endpoint for my interval. But now I've broken this up into my 6 subintervals. So there's 1, there's 2, there's 3 where I stop. You can see my intervals now. 1, 2, 3, 4, 5, 6. So I'm going to be building these rectangles into 6 subintervals. 1, 2, 3, 4, 5, 6. Notice they each have a distance of 1/2. There's 1/2, there's 1, there's 3/2, there's 2, there's 5/2, there's 3. So that's all it's asking me to do, really. So this is the information that I need in order to start building up my approximation using 6 rectangles and the length of the subintervals to be 1/2. So I'm going to save some space here by rewriting delta x for us, and then rewriting x1, x2, x3. So I'm just going to give us some space for the problem. It's 3/2. x4 is 2, x5 was 5/2, and last but not least, x6 was 3. So now I can start filling in the pieces of the puzzle that I need. So we're going to take our sum, and we're going to start from I equals 1 and go up to 6, right? We want x1, 2, 3, 4, 5, and then 6. So we're not doing a limit as n goes to infinity. We're just doing it the way they told us to do it by only using 6 rectangles. and by using that specific set of subintervals, f of xi delta x. So what we want to do is plug in f of 1/2. Right, that's the first x value is x1, which is 1/2. So we want to plug that into our function, multiply that by delta x, which is 1/2. Then we want to move on to x2. Well, if I plug x2 into my function, I'm plugging the number 1 into my function, so I need f of 1 times delta x is 1/2. Right, the delta x is never going to change. Then I want the third x sub 3, so f of x3, well, x3 is 3/2, so I want f of 3/2 times, again, delta x is 1/2. Right, and then I want x4 plugged into my function. Well, f of x4 is the same thing as f of 2. There's delta x. Then I want x5 plugged in, so I want f of 5/2 times 1/2. And last but not least, if I can squeeze it in there, I want f of 3, because 3 is x6. And of course, I have to multiply by 1/2. Now, all of these have multiplication by 1/2. So when you look at this summation here, it's telling you to add the first, second, third, fourth, fifth, and sixth I plugged in. And here it is. Here is the first, here's the second, here's the third, here's the fourth, here's the fifth, and here's the sixth. And what we're going to do is just factor out, since it's this value times 1/2, this value times 1/2, this value times 1/2, and we're adding all those up. Every single one of those has a common factor of 1/2. So rather than multiply by 1/2 each time, I'm going to factor out the common factor of 1/2, and then I'm just going to look for f of 1/2 plus f of 1 plus f of 3/2 plus f of 2 plus f of 5/2 plus f of 3, the right endpoint. And so since they each have a common factor of 1/2, I'm just factoring that common factor out. Now let's go plug these values in and see what we get. Again, using this function, f of x is x squared plus 2. So what I'm going to do is plug 1/2 in, square it, and add 2. And I'm going to plug 1 in, square it, and add 2. Then I'll plug 3/2 in, square it, add 2. Right, and I'm just going to add up all those terms. So when I go to add up all those terms, I get some values in my calculator that I'm basically filling out. Some of them are nice, like f of 1 is really nice because you're squaring 1 and adding 2, so that's why you're getting 3. But then the other ones I'm just writing out whatever the calculator spits out. All right, based on these values plugged into my function, plug 1/2 into your function, x squared plus 2, and you get 2 1/4, right? 2.25. Plug 1 in, square it, add 2, you get 3 output. Right, so you'll just figure out what all those are. I'll add all these together in my calculator, and then I'll divide by 1/2. So I get 1/2 times 34.75, which is 17.375. Now again, when we look at this in terms of the function we were asked to use, so we wanted to go from 1 to 3 of this function. F of x equals x squared plus 2. So we're living above this x-axis here. And when we look, we can relate this to the concept of area, but it's not asking us for specifically area. But it's something that we could relate and sink our teeth into. We can really think about this in terms of area. But again, it's not asking for area, so we're not saying that it's 17.35 or 375 square units. We're not talking about area, so we're just giving it a value. But what we were doing is we're breaking up these rectangles. 1, 2, 3, 4, 5, 6. Right, so we've got 6 rectangles on that subinterval from 0 to 3. Notice I was using right endpoints. When I use right endpoints, I'm getting some over approximation here, over approximation here, over approximation, and just barely a little over approximation. So that is an over approximation because I was using right endpoints on this increasing function. So my rectangles were a little bit taller than the actual curve itself. So when it comes to evaluating this, I'm getting a little bit of an over approximation. So to avoid that, that's when we start looking at the integral. And that is introducing the concept of, hey, why don't you just use an infinite number of rectangles and get the exact amount that you need, the exact number, not some approximation. So what we'll do is the same thing again, but this time we will use the definition of the integral to evaluate the integral from 0 to 3 x squared plus 2 dx. So just remember that number, or maybe I'll jot it down over here, 17.375. And we'll see how close we got with our first approximation versus now the actual value of the integral. All right, and we'll just do a little quick compare at the end. So what we want to do is start by taking this integral from 0 to 3, noticing that the function we're dealing with is the same. We're integrating that same function f of x, x squared plus 2, from the same starting point to the same end point from 0 to 3. So we got a lower limit and an upper limit. And we have to be able to use this in terms of the limit as n goes to infinity of the sum from I equals 1 to n f of xi delta x. So now I'm introducing this concept of, hey, you know what? I'm going to let the number of subintervals go to infinity. That way I'm not just drawing 6 rectangles. I'm drawing an infinite number of rectangles to get the exact, I hate to say area, but it's really the only concept we have so far that we can relate this to. When we talk about integration, it's just its own thing. It's just a mathematical concept. Area is just one of the things that integration is useful for, but they're two separate concepts, truly. Here, we're just looking at the integral, so we're just going to get a number out of it. We're not going to talk about square units or anything fancy like that. So again, delta x, we can compute that by chopping up this interval n times, because it's the entire length of the interval chopped up n times. Notice now we're going to let that n go to infinity. So that's why the length of the subintervals isn't a fixed value like a half, a half, a half, a half, a half. Now we're not doing that because we're letting those subintervals shrink more and more and more and more until we get an infinite number of rectangles squeezed in there. And I guess I'll have to squeeze over here. Each ai plus I delta x is going to be given by starting at the beginning of our interval. We don't want to leave anything out. Plus I times, we just found delta x to be 3 over n. So that tells me that each ai is 3i divided by n. Or 3 over n times I, however you want to write it. So now we can start writing this stuff out. And again, just to have the space over here, delta x is 3 over n. Keep that in mind. And each ai plus I delta x is going to be given by 3i over n. So that's how I'll find each x of I. I said ai. Really I mean xi. Xi, right? There's no a in our function, so I don't know why I wrote a. Sorry about that. We're just talking about xi's. Okay, so that tells us that now we can set this up so that when we evaluate this integral, We are evaluating this Riemann sum, which means we are looking for the limit as n goes to infinity of the sum from I equals 1 to n of f of, here's our xi, 3I over n, times delta x, which is 3 over n. So that means I'm looking at the limit as n goes to infinity of, now, if you look at this summation right here, notice it's letting I go from 1 to n. This delta x that I'm multiplying the function by in each term I sum up doesn't have anything to do with I. It's always 3 over n. So this is just a constant multiple of 3 over n. So I can pull it outside of the summation, but I cannot pull it outside the limit because then I'm ignoring the fact that n has to go to infinity by not including it within the limit. But I can pull it out of the summation of I equals 1 to n. And then I'm plugging in f of 3I over n every time. So I'm looking for this function, f of 3I over n. Here is my function, x squared plus 2. So I'm looking at 3I over n squared. There's each xi being plugged in and being squared and then adding 2. So again, I'm replacing each one of these x's in my function, and then I'm summing it up for the first one, for the second one, for the third one, for the fourth one. So that I is taking care of each one, all the way up to n. So what I can do is, I can square that out. I can look at the limit as n goes to infinity of, again, 3 over n is outside the sum, but it can't be outside the limit. And then the sum goes from 1 to n of, this will be 3I squared up top is 9I squared up top over n squared on bottom. And then don't forget your plus 2. But there was really nothing to do with that. 2 is just a constant, so I'm not plugging in any sort of thing in its place. It's just always going to have that plus 2 term added on. Every time I go through my next term in the sum, there's also that plus 2 just sitting there. So now we can start cleaning this up. We're looking for the limit as n goes to infinity of, we're going to have 3 over n times the sum from I equals 1 to n of 9 squared, which is, or sorry, just 9 over n squared. And we're going to multiply that by I squared. So again, this 9 over n squared becomes a multiple that I can pull out here. But I'm also looking at plus, I'm using this summation stuff to break everything up, 3 over n times the sum from I equals 1 to n of the number 2. Notice there's no I involved there, there's no n involved there. So the 3 over n is being multiplied by all this, so that's why I'm giving each one of these a multiple of 3 over n. You could leave it factored out front and then put the brackets so that it distributes. But I just chose to write it this way. And I'm breaking it up across the addition because this is the sum of like one AI term and a BI term. It just so happens the BI term is a constant, so I just get to break it up and write it like that. Let's pull this outside the summation because it doesn't have anything to do with I. I is going from 1 to some number n, but that's not changing n squared in the denominator here, so might as well just pull it out. The limit as n goes to infinity of 3 over n times 9 over n squared is 27 over n cubed. And now I'm looking for the summation from I equals 1 to n of I squared. Plus, here's 3 over n times the summation from I equals 1 to n of the constant 2. Remember, when you do the sum of a constant, all you have to do is write this as 2 times n. So this is plus 3 over n times 2 times n. Now, we did see a nice formula for this, for the sum of the squares. So when we go from the summation from I equals 1 to n of I squared, we have a really nice formula for that. So I'm going to use that formula to say that all of this calculates to be the limit as n goes to infinity of 27 over n cubed times the quantity. And remember, the formula for this is n times n plus 1 times 2n plus 1, all divided by 6. Plus 3 over n times 2n, it means plus 6. Those n's can cancel out because one's in the numerator, one's in the denominator. Now let's clean this up because we're done with the summation notation using that nice formula. All right. So we can say 3 goes into 27 9 times. 3 goes into 6 2 times. So this is 9 halves. We have this factor of n up top, which can cancel out with one of these factors of n in the bottom, which will leave us with an n squared in the denominator. And I'm going to actually distribute out the n plus 1 and the 2n plus 1, n plus 1 times 2n plus 1, just so we could see maybe a little nicer that we'll have 2n squared plus 3n plus 1 in the numerator. I'm doing that just to show you that, notice these have the same degree, top and bottom. So when I look at the limit as n goes to infinity for this ratio, yeah, you could apply L'Hopital's rule, but this ratio will be 2 to 1 as n goes out to infinity. So we'll calculate that limit a little bit faster. So now we can say, take the limit. Since we're looking at this first piece here, we've got 9 halves times this quantity. Remember, you can pull that 9 halves out of the limit because it doesn't have anything to do with n. But we do need the limit as n goes to infinity of 2n squared plus 3n plus 1 over n squared. Plus, then I can take the limit of this constant, the limit as n goes to infinity of 6. So now I have a multiple of 9 halves. Again, it's pretty easy to show that this limit is 2. You can use L'Hopital's rule if you need to, but that limit is 2. Plus the limit of a constant is a constant, so I add 6. These 2's cancel out. So I get 9 plus 6, which is 15. And the number we got last time was that 17.375. I don't know if you can, yeah, you can see it over there on the side. So we were close with the approximation with 6 rectangles, but like I said, we went over, right? So that was an over approximation, where this is giving us the exact value of this integral. Now I know, and I've already said it, the notation in this section can be a little cumbersome. Here is what we're trying to find, the value of this integral. Here is what we got. Notice how much notation we had to sort of suffer through to get there. So this is where I like to take a nice little aside here and say that if you go back and look at section 4.9 where you talked about finding antiderivatives and how that's useful, is because notice that value of 15. So peeking behind the curtain, what we can end up doing and what we'll do in the next section is show that, and here's where this notation is going to come back into play, that vertical bar notation. What we can show is that if we start using the concept of an antiderivative, look, x squared here. If I anti-differentiate, I get 1/3 x cubed. So back in 4.9, we saw how to find the antiderivative. The antiderivative of 2 is 2x. Watch something funny that happens. Now, I'm not going to say this is a property or a rule just yet because we spend a whole section on it after this. But if I plug in the upper limit and I get rid of the value of the lower limit, which in this case is kind of boring, it's just 0. I'm plugging in 0. So again, we'll talk about this notation in the next section, but I just like to show how nice this is. Like, that's 0, that's 0. 1/3 times 3 cubed, that's 27 over 3, that's 9. Plus 2 times 3 is 6, that's 15. How much better was that, right? We immediately got outside of the notation that we're not worrying about sums or limits or anything like that, and we're getting the actual value of the integral a lot faster. So that's the goal, right? That's the goal, is to get to that next section where we can actually start applying that antiderivative concept. And you're thinking, oh, well, I'll just do that. That's easy. I'll never take a limit of a summation and use those formulas and compute it like that. I'll just always do integration. Well, unfortunately, say we want to evaluate the integral from 0 to 3 of the square root of 9 minus x squared dx. You have to go find the antiderivative of this entire function, not just the polynomial, not just the square root of x, but this is an actual composition of functions. It's a square root of a polynomial. And I'm telling you, you don't know how to do that. If you take Calc 2, you'll learn methods on how to integrate functions like this, but there are some things like this function that you will just, never be able to do by hand. You'll need some sort of approximation by using some sort of, computer algebra system, or, funny things like this. You're just not going to be able to integrate them. So you do have to be careful. There are functions out there that you just can't do it. You can't do it using those antiderivative simple techniques. But, again, don't worry. It's not like I'm going to be throwing things that you can't integrate at you. But for right now, since we can't do this one by finding a general antiderivative, and boy, oh boy, those Riemann sums are really, really cumbersome, the nice thing that we have is that if we look at this function, y equals radical 9 minus x squared, that is the upper half of a circle with radius 3, and we're only concerned about the lower limit being 0 and the upper limit being 3. So what I'm looking at here is the quarter of a circle. Right? The function actually gives me the upper half of the circle. If I had y equals the negative square root 9 minus x squared, then I would get the lower half of the circle. Right? But what I want is to evaluate this integral, which means I could set it up as an infinite number of rectangles buried under this curve. But if we can more quickly identify geometrically that this curve is just a quarter of a circle, now I can relate this to the concept of, oh, okay, well, if I look at the integral from 0 to 3 of radical 9 minus x squared dx, it's going to be 1/4 of the area of this circle of radius 3, which is pi times 3 squared. Right, so the area of the circle is pi r squared, but we don't want the entire circle. We just want this upper right quadrant here from 0 to 3 of this positive function. There's no negative function there, and I don't care about the stuff that's negative over here. I really only care about that spot. So now I've got 9/4 pi. So the value of this integral can be found geometrically, just by simply recalling an old shape that we saw before. So we're kind of relying back on our algebra to say, oh, well, I know that shape. I can just use that shape to my advantage, since I know that the integral relates to that limit as n goes to infinity of that nice sum. And then I can say, well, rather than doing all that work, I have a fixed formula to find that. And I can just apply that formula. So already we can kind of find a way to dance around this, Riemann sum stuff without having to do too much computational work. But not every curve that we come across is going to have one of those nice shapes that has a fixed formula from algebra that we can just plug in. So we don't really get to use that quite often. Only if we come across a very specific geometric shape do we get to do that. So here are some properties of definite integrals. These are the things that we are allowed to do when we come across some definite integrals. The first one being that if we integrate from a to b, a function f of x dx, then we can actually look at the integral from b to a, but it's going to give us the opposite sign of f of x dx. We'll get the negative if we, what they call, swap the bounds, or swap the upper and the lower limit. Rather than integrating from left to right, we're integrating from right to left. You can think about it that way. So we'll get the opposite sign. So you can always do this, flip those bounds, right? But make sure you're negating the function when you flip those bounds. Or if you were to flip them back, then it'd be a negative negative, which means back to positive. So you're always allowed to do that. Next we have the integral from a to b of just some constant c dx, which means we're going to get c times the length of the interval b minus a. Right? So here we're integrating with respect to the variable x, but there is no variable x. It's just a constant multiple. So I'm going to take that constant multiple and just multiply it by however long that interval was that I was supposed to integrate over. Again, what this really shows is, since area is kind of the only concept we have for right now, if I go from a to b with this constant function, I'm finding all those infinite rectangles underneath that constant function y equals c, which is just a horizontal line. So it's not just going to be c, just the number c, it's going to be c times whatever the length of that interval is. So this is just like a very complicated way of writing a formula for finding the area of every rectangle that has ever existed ever. Right? So rather than worry about that old length times width formula, you can just use this every time. No, obviously don't do that, right? We have the length times the width is just two numbers we multiply, so that's obviously the easier method. This is overkill. Third property, if we're integrating f of x plus or minus g of x from a to b, then what we can do is integrate from a to b the function f of x with respect to x, and then integrate from a to b the function g of x with respect to x. Right? And if it's plus, we add these two integrals together. If it's minus in between those two functions, we subtract those two integrals. Basically what this is saying is that, much like differentiation, we can do it term by term. Right? We can integrate term by term as well. So that makes things pretty nice for us. And now we can kind of combine some function and some sort of multiple c times f of x integrated from a to b with respect to x. We can pull that multiple of c out since it is just a number and it has nothing to do with the function x other than it's just going to multiply whatever I have. Whether I multiply at first and then integrate, or if I integrate and then multiply later, I get the exact same result. So we can't pull the function f of x, or any term that has x in it, or any function in here in the integram that has something to do with x. I can't pull it out of the integration because the integration tells me what to do with x. So if I pull an x out, then I'm completely ignoring the integration. All the x's must stay in there because those are the things that need the integration. So we can't leave them behind. Another property, if I integrate from a to b, some function f of x with respect to x, then what I can do is I can actually integrate from a to, I've already used c, I'm going to use some number n, f of x dx, plus then I can integrate from n to b f of x with respect to x. Notice these numbers that I'm just calling n. Basically what I'm saying is, and again, area is really the only concept that we have to grasp onto at the moment, so that's why I'm drawing this picture. rather than integrate from a to b across in just one big shot, what I can do is I can break it up in the middle somewhere. It doesn't have to be exactly in the middle, like maybe ends right here. And I can find this area first, and then add on this area. And again, I'm saying the word area, but really we're just talking integration. Area is only one specific application of integration. But since I'm drawing a picture, you can see what I'm saying. If I do it all at once from A to B, I get everything all at once. If I decide to split it up somewhere and then add those two values together later, I'll get the same values, right? I'll still go from A to N and then from N to B, and then I just combine them together, and I don't lose any information. So that's a really nice property for integration. Well, maybe we'll just make some space because there's a couple more. And we are on 6. And 6 says, if f of x is greater than or equal to 0 on a to b, or if f of x is positive or possibly equal to 0, then the integral from a to b of f of x with respect to x is greater than or equal to 0 as well. Right? If we're dealing with a positive function, then our integration should be positive. Same thing if we turn this around, right? If our function is always negative on the interval we're looking at, then this should always be negative as a result from the integration. Number 7, if we're looking at two different functions, f of x and g of x, and f of x is always greater than g of x on the interval from a to b that we are concerned with, then we know that the integral from a to b of f of x is also going to be greater than the integral from a to b of g of x. If this function always is greater than this function g, then the integral of that function f is always going to be greater than or equal to the integral of that function g. All right, and obviously if we get rid of this and say strictly greater, then we have strictly greater. But I'm just saying that it could also be greater than or equal to, greater than or equal to. Obviously, again, we can flip this around. If this is always less than, then that's always less than once we integrate them. And then last one here says if some value m is less than f of x, which is less than some value capital M, i.e. the value of this function on the interval a to b is stuck in between these two numbers, i.e. I have some sort of function like here is capital M, which is just a constant function. Here is lowercase m, again, just a constant function. And my function f does something funny like this, but it stays in between those two values, means it's bounded up top by this large number, it's bounded on bottom by this small number. Then when I integrate, I still am bounded, but I'm not just bounded by lowercase m and uppercase m. I've got to be more careful about when I look at f of x dx. Let me write this because I didn't write then. Then we would have the integral from a to b of m with respect to x is less than or equal to the integral from a to b of f of x with respect to x, which is less than or equal to the integral from a to b capital M with respect to x. Now what this tells us is, again, we're sandwiched between these two values for our function, but the integration of that function from a to b is going to be sandwiched between these two values. M times the length of the interval b minus a is less than or equal to this, which is less than or equal to capital M times the length of this interval b minus a. So we're not just going to write lowercase m and uppercase m here. We have to integrate everything properly to see where those values come after we've integrated. Okay, now we should be a bulk of the way through all this stuff. Got those. Got those. Got those. Awesome. Excellent. All right, so just wanted to make sure I got all those properties laid out there. So again, for 5.2, we're still looking at Riemann sums, defaulting back to some summation notation. Even when it comes to integration, we still need to break it up and default back to that summation notation. But if you're trying to evaluate some integrals, just remember there are different ways to do it. See how it asks you to do it. It might ask you to use a finite number of rectangles. Then it might ask you to use the definition, let n go to infinity, and use an infinite number of rectangles. But in the next section, I promise you, the actual notation gets a lot easier to handle. So in the next section, we're actually going to get to what we've been waiting for the entire course. If this was a full fall or spring semester 16-week course, obviously we'd be in about week, 13 and a half, 14 or something. So we'd be or actually probably more like week 14 for sure. We'd be hitting on what's called the fundamental theorem of calculus. And you're thinking, wait a minute, the fundamental theorem of calculus, which is the theorem that we all need to know in order to do calculus. Yeah, it took us the entire course of Calc 1 to get to that first theorem of calculus that says this is how you use calculus. I'm sort of exaggerating there, but that's what we're going to start to talk about, and that is where we get to when we start to evaluate. I would have had, I think I had 0 to 3 x squared plus 2 dx. That is where we get to start doing that nicer method of using the antiderivative to our advantage and finding these values very, very quickly. Now, there are things that we're going to do that involve what is just known as strictly integration, which is just a mathematical concept that can be applied to all different aspects depending on what you do. But one of the main things that we'll do, one of the main applications, is area. We're going to talk about finding area. But again, that is just one very specific application. Integration is more of just this mathematical concept. So we're going to talk about area pretty extensively. And remember, area is just going to be like a physical concept that we can touch, feel, we can see it. Integration is just mathematical. It all just lives up here. So that's our goal, is to get to that. So we're finished with 5.2. All in all, really what I want you guys to do is go back and look at 4.9, practice that antiderivative technique, because that's what we're going to need to carry forward. 5.2, just be careful with the notation. It's pretty thick. As far as notation goes, this is probably in the entire course. This is the thickest, right? You got to deal with limits, you got to deal with summations, you got to deal with this brand new integration notation. So it can be a little tedious to get through 5.2. Obviously I'll give you that much, but do the best you can. But know that the important stuff, the really important techniques, and what we're going to be doing for the rest of the chapter 5, and what we're really going to focus on for that last exam is going to be this type of technique. This type of stuff is what we're going to really focus on. Because when you start Calc 2, that's the first thing you do, is integrate, 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 integrate. That first half of Calculus 2 is just basically nothing but integration. So that's why I want to get you guys really prepared for that. So I'll see you in 5.3, and thank you very much.